Hello everyone, this is Dr. Young, and in this video we're going to continue discussing calorimetry, and more specifically we're going to look at the actual calorimeter itself and start including the calorimeter in all of these equations and calculations. So now in the previous one we just said nothing about the calorimeter, right? In the previous videos we've been saying, okay, we have a calorimeter, the sucker on the left, and regardless of whether or not our temperature increases or our temperature decreases, we had no heat flow in or out of the calorimeter. Or in other words, we said that we had perfect or insulated systems, right? So this would be a perfect calorimeter. Or in other words, the heat capacity of the calorimeter is 0, which is why in all those previous videos, I didn't say anything about the calorimeter because we're assuming that there's no heat flow in or out of it. Now, in reality, right, calorimeters really are going to either absorb heat or release heat depending on what's going on. But in the previous ones, I didn't include it. So when we looked at all of our equations, right, when I set up, like, say, for example, the Q of a reaction plus the Q of what's going on with the water, really there's a Q for the calorimeter also, so Q cal, and all three of those would still be set to 0. But now since the Q for the cal, right, if I look at what this term is, this Q would equal the heat capacity of the calorimeter times the change in heat. But like I was saying, if the heat capacity of the calorimeter is 0, that means this term goes to 0, or in other words, this whole term goes to 0. So I didn't include it in any of those equations in the previous video, in any of those calculations. So we saw things like just that the Q of the reaction plus the Q of the water equals 0, right? We had no Q of the calorimeter. Now, of course, in the real world, if I have a system, I have some reaction, some process, whatever it is, and the temperature increases, right? So I have an increase in my temperature here. What's going to happen is that that's also going to heat up the calorimeter itself. So the calorimeter is going to change temperatures too. You're going to heat up your container, or in other words, heat is going to be absorbed into your container. And the opposite is true also, right? If your temperature decreases, everything gets colder, also your calorimeter is going to get colder. So you have Q leaving, you have heat leaving your calorimeter going into that whole system with whatever's in there, whether it's water or just air or whatever. And so now we need to keep that in mind here, right? So now the idea is that we need to know, right, there are actual values for the specific heat of a calorimeter. It's going to be some number. We can determine it through experimentation like we do in lab, or you'll be given it in a question, which I'll show you here in a second. So we will start having 3 Qs here. So again, I'll just do a reaction or transformation here, and the Q of the water that may or may not be present, and the Q of the calorimeter. So let's take a look at what these, how to approach problems that have a calorimeter that has a non-zero heat capacity. So let's look at this question. A researcher wants, maybe I should check these things, right? A researcher wants to find the specific heat of a new metal alloy they made. To determine this, she heats up a 2.03 gram piece of the new alloy to 100 degrees Celsius and places it into 125 milliliters of room temperature water. And that temperature is 22.3 degrees Celsius. If the ending temperature of the water is 48.9 degrees Celsius and the heat capacity of the calorimeter is 45.1 joules per degree Celsius, what is the specific heat of this new alloy? Now that is a lot of words and numbers. And so how am I going to start approaching this? First thing I want to notice, right, is that I have basically 3 things here, right? I have a piece of metal, right? I have this new piece of metal. I have water, right? This room temperature water. And I have a calorimeter, right? So they talk about the calorimeter here and its specific heat. So I've got 3 things. So when I set up my equation, right, I'm going to say, oh, well, I've got the Q of, I'll put metal here, the alloy, the metal. And I've got a Q for the water. What's the heat transfer going to be for the water? And I'm going to have a Q for the calorimeter, because again, I have all of these things. And again, obeying the first law of thermodynamics, I know those all equal 0. Now, this question is specifically asking what's the specific heat, right? What is the specific heat of the new alloy? So I know that specific heat is contained in this metal, right? In this Q for the metal thing, because we're asking about the metal. And so I'll just rearrange my equations so that I solve for the metal. And I'm going to ditch the colors in a second, but I'll keep them for now, right? So now I know that my Q for the metal is going to equal the negative Q of the water plus the Q of my calorimeter. And just like before, we're going to replace these Q's with the variables that make them up. So I'm changing the temperature of a metal. So I know it's going to be M specific heat delta T. I'm changing the temperature of water, so same equation, so negative MC delta T. Oh, sorry, that's not a plus. It's not a plus Q of the calorimeter, it's a minus because I subtracted it over to the other side. And for the calorimeter, I have a heat capacity. So that's the capital C, right? I'll even put the heat capacity of the calorimeter times the delta T also. And then I just need to start filling out this information here, right? So let's start with the mass, right? So the mass of the metal, what is the mass of the metal? Well, they told me that it was 2.03, right? I already have that highlighted in blue. I'm going to start all the way over here so I try to have enough room. What's the heat capacity of the metal? I don't know. That's what we're trying to solve for. What's the change in temperature? Well, the final temperature of the water was apparently of the metal was 48.9 degrees. And it said we started off at 100 degrees Celsius, right? It was a hot piece of metal. And then for the water, looks like we had, 125 milliliters. I know that that's 125.00 grams, because there's 1 gram per milliliter of water at approximately. And I know the specific heat of water is 4.184 joules per gram degree Celsius. And the change in temperature for the water, it also ended at 48.9 degrees. But it started at room temperature, which they told me was 22.3 degrees Celsius. And then lastly, I have my specific heat for the calorimeter. So that was minus, and what was the specific heat again? Yes, 45.1 joules per degree Celsius. And the change in temperature for the calorimeter is the exact same as the water because they were already together. So it's also going to be this 48.9. I'm sorry, I have to go to the next line here, minus the 22.3 degrees Celsius. So I just have to do all those calculations, right? I got to punch all of those into my calculator. And what I end up getting here is, let's see. I end up getting that my 2.03 grams times the specific heat times, what does this end up being? Negative 51.1 degrees Celsius equals, it's like 12, here we go, 12,700 if I'm looking at the sig figs joules. And then I have to divide by each of these to get them onto the other side so I can isolate my specific heat. 51. So if I divide these onto either side, then my specific heat ends up being 122 joules per gram degree Celsius. And I have then calculated my specific heat for this new mystery alloy. It's super high. It's a really, really high. Cool new alloy. Anyways, so I can just solve it that way. Let's take a look at a new problem. So this question is saying if you have 15.04 grams of glucose and it has a molar mass of 180.16 grams per mole, and it has a heat of combustion of negative 2,841 kilojoules per mole, if it's burned in a bomb calorimeter containing 1 liter of water at 24 degrees Celsius, what will be the final temperature of the water? And then at the end, we're given the heat capacity of the calorimeter, told that it is 64.8 joules per degree Celsius. So, same thing. It looks like I have 3 things going on here, right? I could draw a little diagram to kind of help myself out, right? So we're saying that we've got some sort of calorimeter, got a little lid on it. We've got some water, in it. And then we've got some sort of reaction, right? We're burning it. So poof, we've got some reaction. So now we're looking at all of these Qs, right? So we've got the Q of the combustion, and we've got the Q of the water, right? It says we've got water hanging around. And we're going to have the Q of the calorimeter itself. And again, those have to all equal out to be 0. Now in this one, it's asking about the final temperature of the water, so I'll go ahead and I'll solve for water. So I got Q of my water is going to equal the negative Q of the combustion and minus, right, or in other words, negative the Q of the calorimeter. Just like before, I'm going to go ahead and start filling in all of the equations for these Qs. Water is changing temperature, so I use my MC delta T. The combustion is not a change in temperature, that's a process, that's a reaction, so I'm going to use the delta H thing. So I know I'm going to use the delta H, and they give me the delta H of the combustion up there. They said it's negative 2,841. But notice that it's in per moles, right? So it says that it's in per mole. So the thing that's going to go in front of this, whether it's an M or a G or an N, I need to put an N in here. I need to know the number of moles that I have so I can figure out how many kilojoules of energy are released by that. I'm going to have a little work to do. Let's just preview this here because I start in grams. I'm going to have to convert that in a second, but let's keep going. So I use the delta H equation since I'm talking about a process, not heating up a reaction. And then my calorimeter is changing temperature, so I will use the delta T. So I'll use the heat capacity of the calorimeter times its change in temperature also. So let's start filling out this info. Again, I'll start real wide here. How much water do we have? Well, we have 1 liter, so I'll convert that liter into grams. So I've got 1.00 times 10 to the third grams, right? Or in other words, a kilogram. But I'm just keeping it in grams because I know that my specific heat is 4.184, joules per gram degree Celsius, right? It's not per kilogram, it's per gram. So I converted that, that 1 liter into grams. And the delta T, let's see, what's the final temperature? We don't know. So I don't know it yet. So I'm just going to leave that as delta T just because it's kind of easier to work with. And that is going to equal, right, the negative. Now the N we need to figure out how many moles of glucose do we have? Well, I know that I have, and I'll do this up here, I know that I have 15.04 grams of glucose. And they told me that there's 180.16 grams of glucose for every mole. And so therefore, I know that we have, let's see, that would be 0.08348 moles. So that's the number I'm going to put down here, 0.08348 moles. And my heat of combustion they gave me, they said that was negative, now they said negative 2,841 kilojoules. And over here on the left-hand side, I'm in joules. So I can't have joules in one part and kilojoules in the other one. I have to make them the same. So I'm going to go ahead and turn everything into joules. So I'm going to turn that 2,841 kilojoules into joules so that we can cancel out our units. If I do that, that is going to give me negative 2.841 times 10 to the 6th joules. And it says per mole. And that's going to work out great because I'm in mole. And then lastly, for the calorimeter, again, they gave us the heat capacity of the calorimeter. They said that was 64.8. And again, I don't know what the change in temperature is yet. I mean, I don't know what the final temperature of that is yet. That's what I'm going to calculate. So I'm going to leave that delta T. We're going to solve for that. So if I simplify some of these things, let's go ahead and simplify them so we can do the algebra better. I'm going to multiply the 1 and the 4.184, and that's going to give me 4,184, and that's going to be joule per degree Celsius, apparently. That's delta T. That is going to equal, let's see, 2.372 times 10 to the 5th, and again, that'll be in joules. And then minus, so there's nothing really to simplify over here, 64.8, and then times the delta T. So what I'm going to do is I'm going to get my delta T terms together. So I'm going to add 64.8 delta T to that side and this side. So I get my delta T terms together. That is now going to give me 4,248, I believe, delta T's. And again, that's still 2.372 times 10 to the 5th joules. Sorry, and the units for that, I should be keeping the units. Sorry, that number. So the units for that are 4,248, and that is in joule per degrees Celsius. So this should all make sense here, right? When we keep track of the units. So now I've got a number in front of my delta T, and I've got a number of joules. So I'm going to go ahead and divide that number over so I can isolate my delta T. So I'm going to divide by 4,248 joules per degree Celsius. That makes my joules cancel out, and since the degree Celsius is in the denominator and it's being divided by that, then I'll put it in the numerator. And now, so therefore my delta T is apparently 55.8 degrees Celsius. And what I can do is I can expand out that delta T, right? We know it's T final minus T initial. Delta T is always T final minus initial. And I know that I'm trying to find the final temperature. I know my initial temperature, so 55, so I'm running out of room here. I'm trying to find the final temperature. I know the initial temperature was 24 degrees. That's what they told me. And if I just, again, algebraically move that over, so I'm going to add 24 degrees on each side, I get that my final temperature should equal 79.8 degrees Celsius. That should be the final temperature of this water. So it heated it up quite a bit. That'll be the final temperature of the water and the calorimeter because they're put together. So here's another example, right, of being able to find, for example, the final temperature of something, but we're using 3 Qs instead of just 2 because we have an imperfect calorimeter. Let's look at this one last one. You should take a crack at this, see what you can do. But if we read this out, right, so it says when 7.97 grams of sodium hydroxide is dissolved in 100 milliliters in a calorimeter, the temperature of the solution increases 18.7 degrees Celsius. Assuming that the specific heat of the solution is 4.184 joules per gram degree Celsius, and that the heat capacity of the calorimeter is 68.9 joules per degree Celsius, determine the heat of solution, heat of solvation for the sodium hydroxide. So same sort of idea. Again, you should pause here and take a minute and see what you can do, right? We're going to have 3 Qs, 3 things. So let's take a look at this, right? So hopefully you got that we're doing a process, we're dissolving something, right? And we know we're also, another hint that we're doing a process here is that, sorry, I don't know why that just jumped, is that it says is dissolving, we are dissolving something, and we're being asked to find the heat of the solution, right? So we're trying to, that's the term for when you dissolve something. Does it make the solution heat up or cool down? So we know that we have a Q for the solvation, the dissolution of the actual sodium hydroxide, we're dissolving it. And so again, those are called heat of solution or heat of solvation. We have the water that it's going into, and we have the calorimeter that we're being asked about, right? And that all is going to equal 0. In this case, we're being asked to determine the heat of solution, so I'm going to solve for that one. So I'm going to have the Q, what's going on with that dissolving process, right? It's not a thing, it's a process, and that's going to equal the negative Q of the water, and then minus the Q of the calorimeter. So we're going to set this up again, just like we were doing before. What do these Qs look like? The Q for the solvation, or the Q of solution, that's a process. It gave me a delta H. Again, since it has mole in it, I'm going to have to figure out how many moles there are. And then we have the negative MC delta T for the water, and then negative calorimeter, the heat capacity calorimeter times the delta T. And then we just fill in stuff, right? So again, it looks like we need the number of moles of our sodium hydroxide. I don't know how much that is right off the top of my head. So we'd have to do our 7.97 grams of sodium hydroxide. We should know that sodium hydroxide is NaOH, hydroxide's OH minus, Na's plus 1, so we got the formula. And then we just use the periodic table to look up what the individual atomic masses are and add them up. So we see that it's 39.997 grams per mole. And that ends up giving us here, let's see, 0.199 moles. So that'll be that number here. So 0.199 moles of sodium hydroxide. I don't know what the heat of solution is. That's what I'm going to figure out. That's what the question is. And then I can fill in all the other information that I know here, right? So I know that that equals negative mc delta T. We've got 100 milliliters, so that's 100 grams. The C is still 4.184 joules per degree Celsius gram. Delta T, I don't know what the temperature was to begin or end with, but they just told me that the increase was 18.7. So I get to just put in 18.7, right? It increased. It wasn't a negative number, it was a positive number. And then we're going to subtract for the heat capacity here. So heat capacity, they told me that was 68.9 joules per degree Celsius. And again, we heated up, we were just told 18.7 degrees. If I take all those numbers and start to simplify those up, I'm going to get, well, let's leave this here. So 199 moles negative 7820 if I'm looking at the sig figs. And then for the calorimeter, that's 1,290. Looking at the sig figs. So those zeros are not significant. There's only three. Only have 3 sig figs in these numbers. I'll just remember that. Or you could put this into scientific notation. And if those are simplified, let me switch colors here just so that everything looks more together. So I'm just going to take these two numbers and combine them. So I get negative 9,110 joules. And I'm just going to isolate my delta H of solvation, so 0.199 moles. Just doing the algebra here. So I get that the heat of solvation, or heat of solution, is negative 45.7 joules per mole. Now this is a point to realize that they actually asked up here, right, for kilojoules per mole. So I just want to make sure that this is in kilojoules. So my last little bit is I just have to divide this by 1,000. Or sorry. This number was, I skipped a step. Let me do this all for you. The number that you get from that, right, is actually negative 45800 joules per mole. And I need to change that, like I was saying, to kilojoules. Right, so that my joules cancel out. This number ends up being negative 45.8. So apparently that is the heat of solution in this experiment for the sodium, for dissolving sodium hydroxide. If you looked it up, it'd be pretty close to that number. So that's how we do calorimetry when we have a calorimeter that we know the heat capacity of. So we just, same process, we just have a third cube. I hope that helps. Do lots of homework, do lots of practice. If you have questions, let me know, and happy studying.